With addition and scalar multiplication out of the way, we can turn our attention to matrix multiplication. Okay. And we seek to define a notion of multiplying together two matrices. Okay. And in order to do that, our matrices are going to have to talk to each other in a very specific way. Okay. It is slightly looser than when we were talking about addition, right, where they had to be the exact same shape. That's actually not what we want for matrix multiplication. Okay, so say we have two matrices that we wish to multiply together. Okay, we have A equal to some aij's, we have B equal to some bij's. Okay, and what size do we need for these to be able to talk to each other? Well, it turns out, and showing why this is the case is unfortunately well beyond the scope of this course. It turns out that the product of them, okay, is only defined when the number of columns in A is equal to the number of rows in B. Okay, so say A is some matrix that's M by K, then B would need to be, say, K by N. Okay, what's important is that these two are the same. Okay, and their product, right? So when we multiply them together, we get something, say, some matrix C equals A times B. Okay, that is an M by N matrix. Okay, and let's develop how to actually calculate it. Okay, so let's start with some preliminary work. So let's say A1, A2, AN. Okay, so say that is a row of A. Okay, so you scan through, your different rows of A, and you say pluck out that one. Okay, and it's A1 through AN. And then let's say B1, B2, all the way to Bn is a column of B, right? Where I guess I'm calling them n's here and k's here. So I guess I'll switch that just so it talks with the previous thing we wrote better. Okay. So we have this row of A and the column of B. Then the inner product, this is what we're defining here. The inner product of these two, okay, so the row and the column, is what? Well, it's A1 times B1, right? Well, remember, these are all just, real numbers, so we can multiply them on their own freely. It's A1 plus B1 plus A2 times B2 plus A3 times B3 plus ... and all the way up to A sub k, B sub k. Okay, so that's this notion of an inner product of two, right? You're sort of scanning through. I only have one of these lights, but you're multiplying this guy times this guy, and then you're adding this one times this one, then you're adding this one times this one, and so on and so forth until you add that one times that one. Okay. So now that we have this idea of an inner product, it's actually how we're going to define matrix multiplication. Okay. So let's get our setup. Okay. Move that guy down a bit. So let's say A equals Aij, we'll say it's an M by K matrix, okay? And B equals a bunch of Bij's is a K by N matrix. Then their product, we already said this part, is the M by N matrix, which we knew. C equals a bunch ofCij's, okay, where you find some arbitrary element Cij by taking the inner product of the ith row of A and the jth column of B. Okay, and this seems a little confusing, and it does take a little bit to kind of get a handle on it. Okay, and we'll do some examples of this, and you'll have homework, and hopefully through those two, you'll kind of get a little bit more comfort with these ideas. Okay, let's draw ourselves a little schematic of what's going on here, though. So let's say we have, some matrix A that looks like this, and then we have some matrix B that looks like this, right? Remember, this guy is long, so this one needs to be tall, right? Because the columns here needs to equal the rows here. And then that's gonna, I don't know, come out to some guy that looks maybe like that, okay? But if we have some element in here, right, some Cij, our definition says what we need to do is we need to look at the ith column, or the ith row, rather, of A. And that's going to be some set of elements like this. The ith row, okay? And then we're going to take the inner product of that with the jth column of B, right? Or this is our jth column. And if you recall, this inner product is taking this guy, multiplying him by that guy, and then adding this guy times this guy, plus this guy times this guy, and so on across the whole row, okay? So let's do some examples of this, okay? I think we can fit one on this page. Actually, we probably can't fit that on this page. The nice thing about using this iPad is I can use as many pages as I want and, skip them so we don't have to crowd here without wasting paper, which is nice. So let's say let A equal 1, 3, 1, 0, okay? This is 3. We'll say B equal -1, 0, 5, 4, 2, 7. Now let's calculate. Let's calculate two products here. Let's calculate A times B. Come on. And B times A. Okay. So let's take a look at this, okay? Let's start with A times B. We have a 2 by 2 matrix, and we have a 2 by 3 matrix, okay? So we would expect our output to be a 2 by 3, okay? So let's go ahead and run through that. Copying down our matrices, 1, 3, 1, 0. and minus 1, 5, 2, 0, 4, 7. Okay, so how do we find this element here? Right, this is the 1, 1 element, so it involves taking the inner product of the first row of A and the first column of B, right? So it's going to be 1 times negative 1, which is negative 1, plus 3 times 0, for a total of negative 1, okay? What about this element here? Well, it's still going to be the first row of A, but now we're going to do it with the second column of B, right? So we have 1 times 5 is 5, plus 3 times 4 is 12. So 5 plus 12 looks like 17. Finally, for this element here, we're in the first row in the third column. So we're going to take the inner product of the first row with the third column, right? We're going to have 1 times 2 is 2, 3 times 7 is 21, and so 1 plus 21 is 23. Moving down to the second row, this element right here looks like it's going to be the first row and the second column. So we're going to have 1 times minus 1 is minus 1, plus 0 times 0. Next, we're going to have the inner product of this row and this column. Looks like we're going to have 1 times 5 plus 0 for 5. Then for this last entry, we're going to have 2 times 1, which is 2, plus 0. Okay, so that is our matrix, right? That is A times B. What about going the other way, right? What is B times A? Well, here's what I want to draw your attention to, right? If this were possible, we'd have a 2 by 3 matrix times a 2 by 2 matrix. But remember that we said these two need to be the same, right? How would you take the inner product of these of rows and columns of these matrices if that wasn't defined? Okay. So, unfortunately, that means that this is undefined. Okay. Let's do ourselves another example. Okay. And let's deal just with square matrices. So let's say A is 5, 7, negative 3, 0, and B is, say, 1, 2, 9, negative 1. Okay? And we're going to calculate AB and BA once again. Okay? Starting with A times B, okay? It's going to be 5, 7, negative 3, 0, times 1, 2, 9, negative 1. Okay? And this time I'm going to write out the full expansion of what's in each of these, right? So what happens here? Well, it's the inner product of this row with this row. So it looks like it's going to be 5 times 1 plus 7 times 9, okay? And then I guess I'll put down here what that equals, right? 7 times 9 is 63, plus 5 is 68, okay? What's happening on this entry? Well, we have the inner product of this row with this column. So we have 5 times 2 plus 7 times negative 1. So we have 5 times 2 plus 7 times negative 1. 5 times 2 is 10, minus 7 is 3. Okay? And then what happens here? Okay? We're going to have negative 3 times 1. And then it looks like we're going to add to that 9 times 0. Okay? Well, that's going to be negative 3 times 1 plus 0 for negative 3. Okay? And then what happens with this last guy? We're taking the inner product of this row with this column. So we have negative 3 times 2 plus 0 times negative 1. That 0 drops away again, and we're left with just negative 6. Okay? Now let's calculate B times A. And I think the result will be rather interesting. Okay, so B is 1, 2, 9, negative 1, and A is 5, 7, negative 3, 0. Let's take a look at this. Inner product of this row with this column. So we're going to have 1 times 5. Write that a little cleaner. 1 times 5 looks like plus 2 times negative 3. Okay. For our next one, we're going to have the inner product of this row with this column. So it looks like we're going to have 1 times 7. It looks like plus 2 times 0. Putting that into our matrix down here, 1 times 5 is 5, minus 6 is negative 1. The next entry is just going to be 7. And what happens on the second row, right? This entry is given by the inner product of this row and this column. So we're going to have 9 times 5. Looks like minus or plus negative 1 times negative 3, which is just 3. So we're going to have 4 times 5 is 45, plus 3 is 48. And then for our last entry right here, we're going to have the inner product of this row and this column. So that's going to come out to 9 times 7 plus 0 times negative 1, which looks like it's going to be just 9 times 7, or 63. And here's the really important thing to notice here, okay? In fact, I'm going to write it in red. AB does not equal BA, right? We're certainly not in Kansas anymore because all of a sudden, this idea of multiplication doesn't do the very thing that we expect, right? Which is commute, right? You can't just flip the order anymore when you're multiplying matrices, right? And that was a little evident here, right? Because this multiplication was defined and this wasn't. But even when they're both defined, it's not necessarily true that A times B equals B times A, okay? It's actually incredibly rare for it to be true when you're dealing with matrices, okay? So if we lost that property, is there anything that we actually have, right? So let's take a look at these properties of matrix multiplication. So once again, we'll need 3 matrices, A, B, and C. And we'll just say B matrices such that the following products are defined, okay? So when our matrix multiplication is always defined, 2 big important properties hold, okay? We did lose commutativity, but we kept associativity, which again, I would argue is actually, it's a lot nicer to have something that's associative but not commutative than it is to have something that's commutative but not associative. So we have A times B times C is equal to A times B times C, okay? Again, provided that the size of these matrices works out so that these are always defined, okay? If you're dealing with square matrices, you're great, right? The multiplication of an n by n matrix times an n by n matrix is always going to be n by n, right? That's one of the reasons that square matrices are so useful, okay? Now let's take a look at the distributive property, because it might not quite look like you're used to, okay? And it says that A times B plus C equals AB plus AC, right? And that kind of looks like you'd expect, but there's actually a second distributive property that we now need to pay attention to. And that's that if we have B plus C times A, right? That's BA plus CA, right? And the reason is that when we multiply this A in, we have to multiply it on the left, right? Because we can't just switch order. Likewise, when we multiply this A in, we need to multiply it on the right, okay? And this is a really common mistake that people make when they're first working with matrices, because you're so used to everything commuting, right? If we have AB plus say CA, right? Then that is not right. What you can't do is factor an A out here, right? This doesn't work. And that's precisely because A is multiplied on the left here, but on the right there, okay? I'm going to give you two more examples. One that I hope will kind of motivate some of the things we've been doing at the beginning of this week. And then the second one is one of the places where matrices are useful in the wild, okay? Because it actually turns out that matrices are incredibly important, right? The whole reason that the computer you're watching this on is able to function is because these matrices are really understood and just incredibly useful, okay? But before we get to that, here's what I want to show you, okay? Say we have some 3 by 3 matrix, right? And let's make an equation out of it with matrix multiplication, okay? To -2, say 3, -1, and 5, okay? And I'm multiplying it by some 3 by 1 matrix, x, y, z. Sometimes you'll hear these guys called vectors when there's just, when it's just a column like this, okay? And let's say that that equals this matrix, 4, 10, 14, okay? What happens when I do this multiplication, okay? When I do this multiplication right here, what does that matrix turn into, okay? Well, what are we going to get? We're multiplying a 3 by 3 matrix times a 3 by 1 matrix. So our output is going to be 3 by 1. And this first entry here is found by taking the inner product of this row, or this row, with this column. Okay, so it looks like it's going to be x minus y plus 3z. Okay, what's the second one going to be? Well, it's going to be 1x, looks like plus 2y minus 2z. And then our third row is going to be 3x minus 1y plus 5z, okay? And that's still going to equal 4, 10, 14, okay? But remember, when two matrices are equal, they're equal on all of their elements, right? So this means that x minus y plus 3z equals 4, that x plus 2y minus 2z equals 10, and 3x minus y plus 5z equals 14. And this is a system of equations in 3 variables, right? This is why we care about matrices. It's not just that we can use these matrices to represent our system and then do some work on the matrices and go from there, right? Instead, it's actually that our system is a matrix equation, okay? Given any, system like this, you can form a matrix equation like that. Given any matrix equation, you can form a system. These are identical objects, okay? And that also kind of lends itself, right, to why we draw this dividing line when we're forming the augmented matrix, right? You have this matrix right here, right, which represents all of your coefficients. And then you have this matrix right here, which represents your sort of output of the system. We'll probably talk about this at the beginning of next week, but just a quick vocab word for you now. This guy is called the coefficient matrix. Like I said, we'll get into that next week. Okay, so let's get into an example. Okay, so we'll say a physics teacher surveys his class before offering an exam. And gains the following data. I'm going to use some editing magic to make that matrix appear. So here are our matrices, and we want to calculate and interpret AB. Okay, so some piece of matrix multiplication. So let's calculate it first. We'll grab our two matrices. In fact, I will utilize the copy and paste ability. And we'll place these down, and then we'll take a look at what they represent. Okay. So here's what I'm seeing. So we have this first matrix A, and we have the rows are indexed by the number of hours of sleep, right? So, if you slept less than 4 hours, that's all these people, right? 4 to 7 and 7 plus. Then we have exam scores are indexing our columns, right? And each entry, right, is the proportion of these students who got this score, right? So 75% of the students who slept less than 4 hours got lower than a 60%, right? 20% of the students who slept less than 4 hours scored 60 to 80, and so on, right? This one gives you the number, or gives you the percentage of the students who slept 4 to 7 hours, they got a 62 and 80. Okay, here we have our rows are indexed by the exam score, right? And then our columns gives us the number of exams with that particular score, right? This should be, I believe, a 170, not a 120. And so what this means is that there were 80 exams who got less than 60, right? There were 40 exams who got greater than 80, and so on, okay? So when we calculate this, what are we going to get, okay? Well, let's just write this out, right? Noting that we have a 3 by 3 matrix times a 3 by 1 matrix, so we should expect a 3 by 1 matrix out the other side. This is just going to be a, big inner product, right? 0.75 times 80 plus 0.2 times 170, forgot to change it there, plus 0.05 times 40. Okay. Then our second row is going to be 0.6 times 80 plus 0.3 times 170 plus 0.1 times 40. And our last row is going to be 0.4 times 80 plus 0.3 times 170 plus 0.3 times 40. Okay. And when you take these inner products, right, and you run these computations through a little calculator, pick your favorite, here's what you're going to get. I can't quite fit it on that page, unfortunately. You're going to get that the matrix that's the output is 96 103, 95. Okay. So the second part of this question asks us to interpret what this guy means. And I'm going to see if I can get him on this page. Let's shrink this guy. Let's put our matrix right there. Okay. So let's try to think about what we did here. Okay. A, we have our columns by hours of sleep. We have our rows by exam score. And then over here we have a column of total and then a rows of exam score. But if you notice, right, one of the interesting things about this matrix multiplication, right, is if you have, an m by k times a k by n, right, the output is an m by n. Right, so you can sort of, if you want to think of it this way, like the matrix multiplication eats these center guys, right, and leaves you with an m by n, right? And that's precisely actually what we have here, right? We're eating the exam scores; those are going away, and what we're left with is hours of sleep here and total here, right? This is the total number of students who got 7+ hours, who got 4 to 7 hours, and who got less than 4 hours, right? Because we have the percentage who got, these hours of sleep given an exam score, we have the total number of exam scores, we can calculate this matrix here, okay? So that's going to actually wrap it up for this lecture. So your homework hopefully should already be up. And I will see you next week at the beginning of week 10.